How's everybody? Is this a something? Acid derivatives. What's your favorite acid derivative, Sonny? Acid derivatives. Anybody have any questions while we got 10 seconds? Question?
Are you going to show us the mechanism with PCl5?
PCl5?
Yeah, so when it's under reactions of carboxylic acids.
No, we probably won't do that, but you should be able to give it a pretty good try.
Okay.
We did PCl3. PCl5 doesn't have a pi bond, so you're going to be doing direct displacement, more like SN2. Matt?
What is your favorite acid derivative?
My favorite acid derivative? I don't know, that's a big question. How about Lipitor? That's an acid derivative.
All right.
Actually got a carboxylic acid. What else is up there? Allegra. The Fischer. Okay, green is the outline. Making carboxylic acids, reaction of carboxylic acids, we did thionyl chloride. Very basic, lots of basic principles in that mechanism. We also have a white handout, handwritten. And we'll start here. Okay, the main mechanism that we'll have for this test is called nucleophilic acyl substitution. It's another NAS. The other one was nucleophilic aromatic substitution. Both of these NAS mechanisms are very similar. They're both substitutions. They both occur when a nucleophile was reacting with something. One occurs on an aromatic ring, and thus it's NAS. This one occurs on an acyl group, which is sort of generic for a carbonyl. So we have a carbonyl with a leaving group. We can react with a nucleophile, we can replace the leaving group with a nucleophile. It's not SN1, SN2 because there's a tetrahedral mechanism. This carbon is not tetrahedral. This is an addition elimination. Just like nucleophilic aromatic substitution was an addition elimination. Nucleophile adds to carbonyl, and we'll be doing that tons, many times from here on out. Why would it add to this carbonyl? Nucleophile typically is going to have a lone pair. Well, you got a dipole here, and so there's partial plus on this carbonyl. Electrons add to the carbon, electrons move up onto oxygen. Whenever you do a nucleophilic addition, we said that it only takes place typically when you put the anion on what type of atom? Electronegative heteroatom. There you go. Nucleophilic addition puts it here. At that point, what are we trying to accomplish? We're trying to get rid of the X group. At that point, anytime you can make a pi bond and kick off a leaving group, that's easy to do. We can remake the pi bond, kick off the X leaving group. It's probably going to have a lone pair now. And we have an overall substitution by an addition elimination. Your addition is your rate determining step to give the higher energy intermediate. And then you, going back downhill to the neutral product is fast. In which step does the leaving group leave? Second step, just like our NAS nucleophilic aromatic substitution. SN1, SN2, leaving group leaves in the slow step. Because the leaving group leaves in the fast step, again, lots of things can leave. If you've ever seen it with a minus charge, it can leave in this mechanism. Sometimes even carbon can leave. It won't be a plain like methyl or ethyl. Nucleophilic acyl substitution, additional elimination. Remember, if you're going to add a nucleophile here, which bond are you going to break? Weaker pi bond to oxygen or stronger pi bond to leaving group? Weaker bond to oxygen, pi bond. Electrons up, back down, up, down. We can draw a reaction coordinate diagram. The first step is your rate determining step. B is sometimes called a tetrahedral intermediate because the carbon is now tetrahedral. Over here it was trigonoplanar. And then you fall downhill. It doesn't take much activation energy to fall downhill to your final product. I showed this a little bit lower energy than that, but that's not a big point. Leaving groups, you can read about them down here. We'll even see a carbon leaving. That'll be called the haloform reaction. Basically, I've already said that. Just stuff for you to read there. Okay, depending on what the X is, that makes your acid derivative. If X is a Cl, that's an acid chloride or acyl chloride. If X is a nitrogen, that's an amide. If X is an OR, that's an ester. So various groups could be starting material. What we want to look at is the reactivity of the various acid derivatives. Reactivity towards what? Reactivity towards the NAS mechanism we just looked at. And the first step is nucleophilic addition. Reactivity towards nucleophile adding to carbonyl. Your acid chloride is your most reactive. Down, down. Amide is your least reactive. Well, the first step is nucleophile adding. We've got to have partial plus here. Every one of these has a carbonyl pulling. So that's not really going to give you your answer. They all have that. What's the difference? The difference is here we have a chlorine, on that end you have a nitrogen. What does the chlorine do in terms of electronic properties? It can donate by resonance, but just like with the aromatics, a halogen's main effect is withdrawing. So this is withdrawing. So what does that do to that partial plus? Does that kind of quench it, or does it make it even more partial plus? Yeah. So this is even more partial plus. I can do it lots of ways. Okay, it's a big partial plus there. You got two atoms pulling on that carbon. Over here, you got a little partial plus there from the pulling of the oxygen. Well, what is the nitrogen? What's its main electronic property? And it's the same as with aromatics. It's actually a net donator. Because its resonance donation is its major effect. So if you got some partial plus, and this is donating electrons, what does that do to the partial plus? Does it kind of quench it, or does it make it even more partial plus? It sort of quenches it. It's like this carbon's a little bit poor. But it's got a rich friend here, throwing some money at it. It's not that bad, okay? You got more partial plus here, so the nucleophile is more attracted to that. And that's your rate determining step. That's why your acid chlorides are more reactive. Now over here, you can actually draw resonance structures. Now with any carbonyl, you can draw a polarized This just illustrates the polarization of the carbonyl. Oxygen pools, pi bond can be moved up to oxygen, that's a resonance structure. But you can do that for any of these. And in fact, if you go back to our mechanism, the first thing that we could have just did the mechanism like this. We could have just moved the electrons up first, and then the nucleophile could have been added. And you would have gotten your addition product tetrahedral intermediate just like we did before. You can either add it here and move them up, or you can do resonance structure. The resonance structure helps illustrate that some partial pluses there because it's a blend. Over here, resonance structure. But then we can show resonance structure here. These electrons move in. And the donation of the nitrogen quenches the partial plus. Now you might be thinking, can't we draw a resonance structure here and show quenching of this partial plus? Well, you can, but remember, what's the major effect for chlorine? Donation or withdrawing? Withdrawing. Yes, you can draw resonance, but the main effect is withdrawing, and the withdrawing is going to make this more partial plus. So you've got to remember what's the major effect when it can do both. Okay, so there's a different number of ways to kind of look at this. Let's look at esters. Why is an ester more reactive than this? Well, let's say partial plus here due to this dipole. What's the electronic properties of oxygen? Donator, withdrawer? Net. Net donator is group 1 with aromatics. So partial plus here is quenched by this donation. Let's draw resonance structures again. By the way, to get to a resonance structure like this, we can do 2 arrows. And we can do something like this. And we can show the donation by the oxygen towards the carbonyl. I could have drew the intermediate here, and then we say that the oxygen quenches it. Question, which atom is more likely to pump its electrons into the carbonyl? Oxygen or nitrogen? Nitrogen. Why? Nitrogen's less electronegative. It's not as greedy as oxygen. Because it's not as greedy, it's like, hey, carbocation, let me share some money with you, and here you go. I'll help you out. I don't mind becoming plus relative to oxygen, where oxygen is like, I don't think I like this that much. I don't want to become plus, so it doesn't donate as much. Does that make sense? Nitrogen donates more, so more electrons are coming into there, quenching the partial positive. This is an anhydride. We'll talk more about them. Oxygen bonding to 2 carbonyls. Anhydride. We'll have an entire section on them a little bit later. When you have an anhydride, you do have 2 carbonyls, but all of that is going to be your leaving group. You only attack one carbonyl. The other O carbonyl is the leaving group. It's more reactive than this. So here you have an oxygen. Here. Why is this? Did I say less? I don't know what I said. This is more reactive. Why?
Donates both carbonyls.
You get a little partial plus here. You're saying, well, this oxygen can quench it. I mean, that one can. It can donate and quench it. Apparently, this one doesn't donate as much. That's why it's more reactive. Why does it not donate as much?
Can go to either side.
Because it's busy donating the other way. Okay? It's like two-timing. Okay? It can't put all its electrons this way because it's busy putting some of its electrons that way. So that's why this oxygen cannot donate as much as this one, and thus this anhydride is more reactive, more electrophilic. But when you get to chlorine, chlorine certainly doesn't like to donate, and its net effect is actually withdrawing. Okay, there's a divide right here. Acid chlorides and anhydrides typically are so reactive that they're considered mainly reagents. Reactive reagents, reactants. These also react with just pure water. Or to be a nucleophile has a lone pair. Those are reactive enough to react with just neutral water, fairly weak nucleophile. Esters and amides don't typically react with pure water. They're not as reactive. Water does not add to them. These are reagents. You rarely find these in like natural products out in nature. Why not? Because out in nature it rains sometimes and water comes into contact with and it reacts. Okay? These you find in natural products. You rarely find these in drugs because they're not stable when they get into contact with aqueous systems. These are more in drugs. Okay? These are more your reagents. For example, in lab, some of you have used acetic anhydride, which is this right here. Or we have acid chlorides. They supply acyl groups. We'll do more of that. Okay, most everything I showed is on this page. We showed a resonance structure down here, over there for amides. Resonance is here. Y'all believe this resonance stuff? Been talking about it for a semester and a half. Don't believe it? Would you like some proof? Okay, glad you asked. Here's an amide. It's called DMF, dimethyl formamide. It's a common solvent. You can show polarized with a plus, then you can show these moving in. I showed it all in one step here. Amides have a significant contribution of this resonance structure because that nitrogen donates a lot. Thus, when you see an amide here, there's lots of partial minus here coming from that resonance structure. It's actually partial plus here. Lots of partial minus. Of course, the true structure is a blend here. And nitrogen likes to donate a lot. This oxygen's greedy. It's like, bring it on. How many signals in an NMR do you expect for this here? To answer that, just, what if that's a carbon with maybe an H on it? How many signals for this? 1. It should be equivalent, like an isopropyl group. Well, with a nitrogen, they're still equivalent, perhaps. 1 signal. But if you look over on the next page, there's an NMR of DMF. How many signals do we see from the methyls? Actually 2. You also see water, you also see the H that's on the carbonyl, sort of like an aldehyde proton. Why are the methyls not the same? If this is the true structure and it's like this, and this is a single bond, you should have free rotation. Free rotation should make these equivalent, just like in an isopropyl group. But do you really have free rotation here? Is it really just a single bond? No. We really have pi overlap. Isn't there a p orbital here and a p orbital here? And then this lone pair is in what type of orbital? It's in a lone pair. Okay, you have pi overlap all the way through here. Sort of indicated here. See, there's pi overlap here. What does the pi overlap do to the rotation of this carbon-nitrogen bonding? It can no longer rotate. And if it can no longer rotate, one methyl is cis to the oxygen, one is trans. If it can't rotate, the methyls are different. The NMR tells you they're different. That must mean that they can't rotate. Well, they can't rotate because of resonance donation. The NMR is sort of some evidence that there's some donation there. Pi bonding. Does that make sense why there's 2 methyls? Take home, with amides, the resonance donation from the nitrogen is a major effect. It makes them less reactive towards acyl substitution. Also helps explain a couple other things. Okay. Interconversion of acid derivatives. You can only convert to a less reactive derivative. Now, if you have an acid chloride, you can convert to the other 3. And there may be more acid derivatives, but these are the kind of the ones we're showing right now. But aren't all 3 less reactive than this? That means you can convert to all 3 of those. In contrast, if you have an ester, you can only convert it to what? An amide. For example, you cannot take an amide and convert it to an acid chloride, because that is breaking the rule. That is not a less reactive derivative. It's a more reactive derivative. Now, I'm talking about converting directly. We can convert this to this indirectly with multiple steps, of course. Talking directly. So why does this reaction not work? That's right here. First, your reactivity scale. There's just not a lot of partial plus here, as we explained earlier. It's kind of very generic. We've already kind of explained that. And just saying that it doesn't occur sort of is why A is there. Very unreactive acid derivative. CO minus, even though it's an anion, is a fairly poor nucleophile. It's not great. Can react as a nucleophile, but it's not great. So even at the outset, you've got difficulties. Lazy nucleophile, fairly unreactive carbonyl. But even if we could get this to do this, what does that give? Well, I'll keep the end here. even if we could get it to do that, and get our tetrahedral intermediate, and we say we're going to reform carbonyl, which one are we going to kick off? Nitrogen or chlorine? Chlorine's your better leaving group. And even though this is a fast step, you still want to kick off your best leaving group. So it's just going to do this and come back here. So even if you could get it to react, it's not going to kick off the right leaving group. So that's sort of all explained here. Compare the other way, reacting acid chloride with ammonia. First off, you got lots of partial plus here, as we explained. Very reactive carbon. You got a pretty good nucleophile, ammonia. It's actually stronger than Cl minus, even though it's neutral. So this will add. I lost an H. Everybody's noticed I lost an H. There's 3 H's here. Where'd the H go? There's really we had to lose an H there. Okay? And throughout this chemistry and all the way through the end of the course, we'll have to deal with a proton along the way. Now, at this point, whenever it comes down, which is a better leaving group, Cl or nitrogen? Cl. So you lose the Cl, you get your amine. So everything is in your favor there. There's just some examples. Acyl substitution, please look at them. You may come back to that. A few other things there. Okay, back over to the green sheet. So what's the name of the main mechanism we're doing here? Nucleophilic acyl substitution. Don't forget that. When we start doing the mechanisms, it'll be kind of hidden in there because we'll do lots of proton transfers. But at some point, we're going to add to the carbonyl, electrons up, and then at some point, we're going to come back down and kick off the leaving group. Okay? But it may be a total of 5 or 6 steps instead of just 2 because we got a couple of other things going on. Proton transfers. Okay, carboxylic acid reactions. Conversion to esters. The most common way is to do a Fischer esterification, spelled with a C. Take a carboxylic acid, treat it with an alcohol and an acid catalyst, you can get the ester plus water. Now if I starve this oxygen here, that oxygen is now there. That is, one of these oxygens is lost. This is not just putting an R group on that same oxygen. One of the oxygens is lost. I would say, hey, that oxygen there is lost, but it actually could be that one. Because at some point in the mechanism, these will become equivalent. The acid can be sulfuric acid, it can be HCl. You can also use para-toluene sulfonic acid. Have we used para-toluene sulfonic acid in here? Some of you have already used it in the lab. We used it with the diazonium reaction. It's tosyl acid. Toluene, and that's tosyl chloride we used to make tosylates a while back. Tosyl acid is just OH. So it's a benzene sulfonic acid. It's a solid acid, so that makes it convenient for weighing out. If you drop it, it doesn't run all over the place. And it's also dry, or it can be. In lab, you use the hydrate, if you remember. You have 1 mole of water associated with it, but you can make it dry. Okay. Basically, the goal here is to replace the OH with an O-ethyl. Mechanism. Very important. Whenever you're doing carbonyl chemistry and we're under acidic conditions, the first thing you always want to do is protonate the carbonyl. This is really true with any mechanism. Any mechanism where you're under acidic conditions, the first thing you're probably going to do is protonate something. What do you want to protonate? Which oxygen is more reactive, top or bottom? Look back at your thionyl chloride reaction. Which oxygen did reacted with the thionyl chloride? Remember I said you want me to lie to you or not? Which oxygen? Top one. Because if you do resonance structure, that has partial minus and that has partial plus. Do resonance structure. The top oxygen, H plus. Okay, first step is to protonate the carbonyl. We'll call that phenyl. 1 lone pair, that's now a positive. Okay, protonate the carbonyl. This reaction doesn't take place without the H plus catalyst. That means don't do anything until you first protonate something. Now at this point we have our nucleophile, ethanol. Okay, what does protonation of the carbonyl do? That oxygen's pulling. Okay? It's like I need some electrons, so I'm going to pull. Is this oxygen going to pull more or less? This oxygen is now mad and it really wants some electrons. Now that oxygen is going to pull even more. It's like, okay, you made me mad, I'm really going to pull now. Protonating the carbonyl makes the carbonyl more reactive towards nucleophilic addition. Now we have lots of partial plus here. We could just illustrate that like that, or we could do resonance structure, where this oxygen is like, okay, I'm greedy, I'm just going to pull this up, and I'm going to just give, okay, how about that carbon? I'll just leave you with no octet, because I like electrons, I want to be neutral, boom. See, ethanol is a pretty weak nucleophile. It won't add to the carbonyl that readily. But if we protonate it, now there's lots more plus on this carbon. Now the ethanol will add. Which resonance structure do you want to add to? Camille? First one? Okay. You can always work with any resonance structure. We add to the first one. We add here. We move electrons up. There's the error already. What does that give? We need to be more careful with our groups. A lot of people are putting stuff like this. Okay? This is pretty much meaningless. What's bonded to this carbon? The ethyl? I'm not sure. Okay, please be more careful. The oxygen's bonded, that oxygen has an H, it has an ethyl. I'd probably draw it out like this. There's one lone pair left, and by the way, that's a plus charge. So what did we just do here? There's our nucleophilic addition. I could have also have added it right there and gotten that. Let me ask you this, which is the major resonance structure, left or right? That one, more bonds. More bonds. Okay, nucleophilic addition. What are we trying to accomplish here? Trying to make that plus what? Plus water. Okay? We somehow have to eliminate water. What do you want to do next? Now, you see how the two oxygens become equivalent in the mechanism? See how they're the same there? I'll have to just go ahead and show you. We want to eliminate one of these OHs. How do you make an OH a better leaving group? Protonated. Do we have a proton? Yes, there's a built-in acid right there. It looks like H3O+. We can do a proton transfer. I'm not going to show any arrows. And we get which H do you want to put this, which oxygen do you want to put this H on? Huh? Top or bottom? Okay, let's put it here. Okay. What do? We transferred the proton from one oxygen to another. I mean, why should this oxygen keep the H+? That oxygen is just as basic. Okay? Now at this point, what are we trying to accomplish? We want to eliminate the water. We have electrons here. Anytime you can make pi bond and kick off a leaving group, that's pretty easy to do. What does that give? I bond to oxygen, but there's an H there. And then we have what? O ethyl? Plus what? Plus water? And look where we're at. What do we need to do to get a final product? There was a minus here. Para-tosylate minus. Go with that. This O minus can take the H, leave the electrons behind, we get that plus what? Plus our catalyst reformed. And what do we ultimately do? Ultimately, we replaced an OH with an O ethyl. Ultimately, we did an acyl substitution. But we have proton transfer at the beginning, we have proton transfer in the middle, and we have a proton transfer at the end. Nucleophilic addition, what do you want to call this step here? We'll be able to eliminate the water. Elimination. How's this look? Now, this is the true equilibrium reaction. Every step up here is reversible. That is, if you have an ester, can you protonate the carbonyl if you have a strong acid? And go this way? Certainly, why not? We protonated that carbonyl, why not protonate this one? And if you protonate that carbonyl, could water add to this, electrons up, to give this addition product? Sure. And if it did, could the proton then transfer to that oxygen? Give this? Sure. And at that point, could these electrons move in and kick off the ethanol? Sure. And at this point, could something take the H and go back to this? Sure. This is a true equilibrium reaction. Every step is reversible. In fact, later on, we will, what is the reverse? You take an ester and you get what? An acid. The reverse is shown here, where anything in the box, including a ester, can be hydrolyzed back to the acid. That's just the reverse of what we're doing. Now, since it's an equilibrium reaction, we have to drive the reaction one way or the other. Question: how do you drive this reaction towards the ester? Somebody tell me how you would do this. Remember Le Chatelier's principles? How would you drive this reaction and make it go all that way? Do what? A lot of this? You got to be careful, because when I say drive it, I mean make it go 100%. You can't say I'm going to drive it by adding more of this, because you'll just be left with more of that at the end. Removing water. If you remove water, it will drive it this way. How would you remove water as it's formed? Heat it with the idea of what happening? Water boil out. What's the boiling point of water? What's the boiling point of ethanol? 78 degrees. Which is going to boil out first? Your ethanol will boil out first, so it's going to be practically not possible. Drying agent. What type of drying agent? You might throw in some sodium sulfate. Maybe once it's formed, it'll soak it up and effectively remove it from the equilibrium. Molecular sieves. Those are kind of a drying agent. You don't want to add excess this, because this is your reactant and you'll just be left with it. You can't say I'm going to consume it. I mean, if you have 2 millimole, 2 mole, and in equilibrium you have, it goes 50% and this goes down to 1 mole. So at equilibrium it does half. You can't say you're going to drive it by making this 4 mole, because at 4 mole you'll be left with 2 mole. It's still going to be half, so you can't just increase that. But what could you increase? Ethanol. Usually this reaction is done where you use ethanol not only as the reactant but also the solvent. So there's a huge amount of ethanol there. And a lot of one of the starting materials will help drive it. And usually that's the most common way to do it. Because of that, you usually use small alcohols, methanol or ethanol. Ones that you can get rid of at the end. We do need to think about driving it. Question: how would you drive the reverse? If you had an ester and you want to go that way, how would you drive it that way? A lot of water. And acid. And collectively, what is water and acid called? H3O plus. We'll drive it the other way. That's why on the handout over here it says an ester will react with H3O plus to go the other way to the acid. Fischer Esterification. Another way to make esters. 2. This is going to be more straightforward. This is going to be more kind of old-timey chemistry. We actually covered this reaction in Organic 1. You can take an acid, treat it with base, and then come in with an alkylating agent, and you can make the same ester. What does the base do to the acid? Deprotonated. What's your favorite base? KOH. That's plus, that's minus. Hydroxide takes the H and leaves that behind. We get that plus water. We throw in ethyl iodide, what will this do? Good old SN2. That's just a good old SN2 where you use the carboxylate anion as your nucleophile. And we did that in Organic 1, right? But that is another way to make an ester. In that way, is that oxygen new? In this way, that's the same oxygen. Right? That would be called an O-alkylation of the carboxylate. Okay, both of those are esters. What else can we convert the acid to? By the way, remember, everything we do is back here. So we converted to acid chloride. We just converted to esters. Now let's look at converting to anhydrides. Here. So this is an anhydride, oxygen with 2 carbonyls. It's a mixed anhydride because the R groups on the sides are not the same. One way to make those is, now, word of advice here, there'll be lots of reactions. You've got to see what the basic mechanism here is. And for example, I would expect you to already be able to show this product by me just giving you that. Already. Let's look at it. What will the base do to the acid? Let's use a different base. How about an organic base like, what is that? Triethylamine. That is strong enough to take the H. And we get a carboxylate. We throw in the acid chloride, what could it do? Acid chlorides are attacked by nucleophiles. We have a nucleophile. Yes. This will add here. Mechanism, what happens? Electrons up. And I'll come here. See, at this point, we're basically starting to review from here on out for all the next examples. What does that give? Big nucleophile, added to the carbon, electrons up, minus, there's a chlorine there. What am I missing? Yes, that should be neutral. I'm missing that methyl that is on there also, yeah? What do you want to call that? Addition? What do you want to do next? Do I have a proton I need to worry about? No. Make pi bond, kick off the chlorine, Because you have to recognize if I kick off the chlorine and do this, what does that give? There's your product. And basically, what used to be under my hand? Chlorine. What's now under my hand? The nucleophile. We did a nucleophilic acyl substitution. But I would expect you to predict that product anyway, because you say, okay, base is just going to deprotonate. I have nucleophile. Acid chlorides are attacked by nucleophiles in this manner, and you should be able to just predict that product. Okay, please look ahead. You have things to fill in on arrows here, and then start doing more reactions. Chemistry of acid chlorides next time. We've already done some, because that right there was an acid chloride reaction. Wednesday I'll get here at 7:30, and I'll go over the Suzuki mechanism. And after that, take any other questions that you want to ask. Wednesday at 7:30, if you're interested. In lab this week, please pick up NMRs. You start looking at the report guidelines for the lab.